was doing better alone, but when you said hello, I knew that was the end of it all. I should have stayed at home, 'cause now there ain't no...
In this series of videos, I would like to discuss series, section 11.2 in Stewart's book. So what is a series? A series is the sum of the terms in a sequence. We have some sequence, AN, so it's A1, A2, A3, A4, A5. And S, our series, is the sum, A1 plus A2 plus A3 plus A4, or written in the sum notation, a sum from n equals 1 to infinity of AN. So for example, when AN is given by 1/2 to the n, this geometric series, which is something we talked about in the last series of videos, well, what do we get? So S equals 1/2 plus 1/4 plus 1/8 plus 1/16. And we have infinitely many things we're adding up. One helpful idea is to keep track of what the sum is equal to so far. So far we have 1/2, then we have 1/2 plus 1/4 is 3/4, then we have 3/4 plus 1/8, which is 7/8, 15 over 16, and you can see that the sum so far seems to be getting closer and closer and closer to 1. And in fact, as you add more and more and more terms, you get a sequence of these partial sums. These sums so far are called partial sums because we're not adding the whole sequence. It's just a part of the sequence, and this is equal to 1. So we'll come back to this later in the video when we talk about geometric series in general. Let's do another example. Let's look at AN equals n. So now what does our series look like? Well, we have 1 plus 2 plus 3 plus 4 plus plus plus. And as we go along, here we have 1. Here we have 1 plus 2 is 3. 1 plus 2 plus 3 is 6. And it's clear that as we add more and more and more things, the number that we're getting as we add what we have so far, these partial sums, we get a sequence that's going off to infinity. So this sequence, we add up all the terms and we get something finite. We're adding up infinitely many things, but we're still getting a finite sum. Here we're getting an infinite sum. Let me talk about one more example before I give a key definition. Let's say AN is -1 to the n. So then our series is -1 to the 1 plus -1 to the 2, which is 1, plus -1 to the 3, which is -1, plus 1, plus -1, plus plus plus. And if we keep track of the partial sums, the sums so far, we have -1, then 0, then -1, then 0, then -1, then 0. This switches back and forth, and the limit of the partial sums, these sums so far, does not exist because it fluctuates between -1 and 0. Okay, so I'm going to pause and erase, and I'll give you a definition that should seem really familiar because we have a similar definition for sequences and one that came up for improper integrals. And then we'll talk about geometric series in general. So that is a series that comes from a geometric sequence. Let's start with an important definition. If our series S is plus or minus infinity, meaning if the limit of the partial sums is plus infinity or minus infinity, like we saw with this sequence AN equals n, or if that limit does not exist. We saw an example where AN was -1 to the n, and the partial sums, the sum so far, fluctuated back and forth between -1, 0, -1, 0. So S does not exist. Then we say that S is divergent, just like we said a sequence could be divergent. Otherwise, if S is not plus or minus infinity, or the limit doesn't exist, then the partial sums, the sums so far, have to be approaching some finite number, L, as a limit. And we say that the series converges, it's convergent, and it converges to L. So the goal for the rest of this lecture will be to calculate some series. And the first big example that we're going to start with is geometric series. So the first example we gave was an equals 1/2 to the n. And we said the sum of this series was equal to 1. So now I want to explain why that is true. So this involves a trick, like a really nice trick that you should know. So we're going to take a series S, and I'll start with an example of, let's say, S starts with 1, and then you have 1/3, and then you have 1 over 1/3 squared. Sorry, 1/3 squared, 1/3 cubed. So this is a geometric series with r equals 1/3. The ratio between every consecutive pair of terms is 1/3. You get from one term to the next by multiplying by 1/3. So if this is S, the trick is, what is 3S? Let me move this over a little bit. What is 3S? Well, 1 times 3 is 3. 3 times 1/3 is 1. 3 times 1/3 squared is 1/3. 3 times 1/3 cubed is 1/3 squared. 3 times 1/3 to the 4th is 1/3 cubed. And so on. The idea is we're calculating 3s by taking each term and multiplying by 3. We're just applying the distributive law for multiplication. So the tricky idea here is, what is 3s minus s? Well, there's a 3 here. There's no 3 up here. But there's a 1 here and a 1 here. So we subtract and they cancel out. And there's a 1/3 here and a 1/3 here. And we subtract and they cancel out. And a 1/3 squared here and a 1/3 squared here. And we subtract and they cancel out. And so on. So every single term cancels except the 3 at the beginning of 3s. But what is 3s minus s? Is 2s. So that means that s equals 3 divided by 2. It's actually going to be helpful to rewrite this very slightly. This is the same as 1 divided by 2/3, which is the same as 1 over 1 minus 1/3. Why did we rewrite it this way? Well, this 1/3 here is the same 1/3 that we're multiplying by to get from one term to the next. So you don't need to know how to prove this, but the idea is just to take the argument that we just went over for the one example where r equals 1/3 and do it for general r. So if s equals 1 plus r squared plus r cubed plus, this series is equal to 1 over 1 minus r. But this is only valid when the series converges. You can see that if you put in like r equals 1, you're getting 1 over 1 minus 1, which is 1 over 0, equals 1 plus 1 plus 1 plus 1 plus 1. That doesn't really make sense. And if you put in r equals 2, then you'd have 1 plus 2 plus 4 plus 8 equals 1 over 1 minus 2 is -1. And that doesn't make sense either. So this is valid for when this series converges, which is when r is a number between -1 and 1. Okay, so this is a really important formula to know. This is going to be one of our building blocks for understanding sequences when they converge and when they diverge. So this series converges when r is between -1 and 1. And another way of saying this is s diverges when the absolute value of r is greater than or equal to 1. So I'll pause and erase, and then we'll do 2 examples, and that'll be the end of the first video. Let's look back at this very first example from this video. Let's take the sum from n equals 1 to infinity of 1/2 to the nth power. So this is a geometric series where we have 1/2, 1/4, 1/8. R here, the ratio between consecutive terms, is 2. Well, one thing we can do is we can factor out a 1/2 and write this infinite sum as 1/2 times, now 1/2 divided by 1/2 is 1. And 1/4 divided by 1/2 is 1/2. And 1/8 divided by 1/2 is 1/4. And this goes on. And why did we do that? Because we know by this result down here that 1 plus 1/2 plus 1/4 plus 1/8 plus, this is equal to 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. So that means that this series is equal to 1/2 times 2, which is 1, which is the formula we gave at the beginning. So one thing to be a little careful about, I know you might look at a geometric series like this one and immediately want to apply this formula. But you can't apply it right away, because in this formula, the first term in your series, the first term in the sequence is 1, then r squared, then r cubed. And here, we're starting with 1/2 and not with 1. So there's this extra algebraic step where you factor out 1/2. That's why I said this is a building block. So we start with this formula, and now we can get formulas for related infinite series. So let me do one more example, and that'll be the end of this video. Let's look at the sum where n goes from now 0 to infinity of 2 to the 2n power times 5 to the 1 minus n power. And the idea here is this doesn't look quite like this, like something to the n power, at least not at first. So you have to first do a little bit of algebra in order to rewrite this in a way that makes it look more like this initial geometric series. So one idea is, what is 2 to the 2n? That's 2 to the 2 to the n. And what is 5 to the 1 minus n? That's 5 times 5 to the minus n. So this 5 we can factor out now. So we have 5 times the sum from n equals 0 to infinity. You can factor a 5 out of an infinite sum like this, just like you can with numbers using the distributive law. And now we have a 4 to the n, 2 to the 2 is 4, times 5 to the minus n, which is the same as 1 over 5 to the n. So what is this? This is 5 times the sum from n equals 0 to infinity of 4 to the n over 5 to the n, which is the same as 4 over 5 to the n. So now, this is in exactly the right form to apply this formula. This is 1 plus 4/5 plus 4/5 squared plus 4/5 cubed. So what we get is 5 times 1 over 1 minus 4 over 5. It's easiest to rewrite this as 5 times 1 over 1 over 5, which is 5 times 5, which is 25. So again, we've used this initial formula as a kind of building block. Starting from here, we can take a more complicated looking series, do a little bit of algebraic manipulation to get it into a form where we can apply this formula to get the answer that we're looking for. So we're going to continue to see geometric series come up throughout this long section of the course about series. So we'll come back to examples like this a little bit later.